Do you remember in the previous a lot of previous videos ago? Okay, we talked about the delay, right? At the very first part of the video, we actually show you. So I think I hope. Let's come back to this thing. Okay, this is when your intro to why nycrisplot is the very first part where we start nycrisplot. Is the very first video. As you can see, we input a sine wave. Okay, so this is the initial sine wave. If you were to go through a transfer function and again, you eventually have a result, right? And then you compare. So it's about there, as you can see. As you can see, once I reach it in that manner, you can see that my there's a phase angle. As you can see, if you were to zoom in, right, the yellow and the purple color is significantly there is certain lagging, right? The purple color is lower than the yellow color. Purple color means that you are going through the transfer function, okay, which is shown, as you can see, which is over here, okay, this transfer function you go through. So in this video we're gonna talk about delay, okay. So in this case, clearly, okay, there is a delay in this section over here, right? The purple color has a delay of a certain phase angle. Okay, so with this said, let's take a look. Okay, what is actually the delay? Okay, it's a very long one, but not long, but rather than, yeah. Okay, so a time delay is common, and then this is the story. Remember in your math, right? In your mathematics 2, and we talk about the delay, okay, t minus a. If you still remember the video on, I mean not video, but rather than the delay formula for Laplace. If you were to change it from the time domain into a Laplace domain, it's actually e minus as, right? If you can barely remember the delay equation, maybe I should show you. Hold on. Okay, apparently it might be some kind of softer voice, but just take a look. Okay, this is the delay. Can pretty much understand things. So apparently, I think we have a graph like this. A function one, for example, at time 0, okay, this is time, x is time, then this is the whatever function. I mean, y is something else, okay. And then for time is 0, the function 1 is started, and then until certain time, until certain time, we call it t1. The function 1 is being destroyed. I mean, is being eliminated, and then f2 function 2 comes in, and then function 3 comes. At this point, function 2 is being eliminated. Function 3 comes in. Okay. So with this said, the relationship for this phenomenon is being written over here. So what it means is that for function 1, this is the function 1 multiplied by ut, okay, which is, if let's say if you have this is a second shift theorem. So let's say if you have this is t minus a. So if let's say you have t when your actual time is at t, so let's say I call it this is a, is it? Okay, no, this is maybe let's call it what, I call it t1, and I call it t2. That'd be cool. And then this is 0. So apparently, or maybe we call it t. Okay, so t is actually the time when you start the thing. Okay, the time when you start, when you on the engine, and vroom, and then F1 will comes in. Then until T1, F1 down, and then F2 up. And then until T2, F2 destroyed, and then F3, this F3 lah, okay? F3 will be up. So this means that F1, ut, meaning that this means that it's the function start at this point, the very original point. And then for you add f2 minus f1, which is the function of 2 minus function of 1, so you will get, because function of 2 is this whole thing, right? Minus function of 1, you get this portion. You get what I mean? So function of 2 covers all this portion. So minus f1, you have this portion over here. So this is what it means. So this portion
it's being represented by, in the time domain, it will be u, and then t minus t1, which is, let's say this is 0. When you start at 0, it's just 0. When you start at it's just 4. Okay, so at okay, this is a little tricky. Okay, let's don't look at. Okay, so therefore, as t1, okay, this is t1. Okay, t0 minus away. Okay. Yeah, this is really tricky. To my best knowledge, okay, I may not know. T minus t1 is actually maybe 4 seconds, right? So 0 minus 4 is actually minus 4. So actually, you're starting at a minus 4 second type of thing. So you actually delay. You have a delay of 4 seconds in a certain sense. Okay, I may be wrong. Yeah, actually, yeah. So this is just a concept only, just saying that there is a delay. Okay, function 1 starts from here, and then at this t1, function 1 is being off, so function 2 is being started. Okay, so this is how it goes. So there is a delay of t1, then function 2 starts. So the delay can be expressed in u. So this is the form. Okay, t minus a, right? It's equals to e minus as. So I rumble all around for this thing. So this is where the delay comes from. Okay, e minus as. And then if you were to do a Euler's method, okay, e minus as, if you were to have a s equals to j omega, you have e minus j omega a. And this is actually simply the Euler's method. Okay, if you were to take a look. Actually not Euler's method, but Euler's formula lah, okay. So ej omega t is equals to cosine omega t plus I sine omega t. So in this case is this is minus, so it's cosine omega a minus j sine omega a. It's just the manipulation, that's all. Nonetheless, you can see like, okay, it's, yeah, I think you know what I mean. Yeah, I believe you already know. So this is just simply the Euler's formula. Okay, and then after that, if you were to have a magnitude of it, okay, because this is a real number, this is an imaginary number, right? This is j. So in the real and the imaginary, you have to find the magnitude of it, because this is actually the magnitude, right? So if you were to do a magnitude, the trigo rule, okay, you eventually get equals to 1. Okay, this explains why this also explains say that this obviously has a magnitude of 1. Okay, when considered in the frequency domain, we replace s with j omega with frequency response of the delay is therefore e minus j omega t, right? Which is what we've shown over here, e minus j omega a lah. Okay, so the magnitude itself is comprised of Euler's formula of the real axis and the imaginary axis, right? And if you do a magnitude, okay, modulus, you have a magnitude of 1 as being proved over here, right? Cosine omega a square. Okay, it's just this is the trigo rule lah. Okay, so therefore you get this one equals to 1. And then if you were to remember our complex number understanding, previously we solved a lot of complex number, right? If you remember, this is the magnitude. Finding the phase angle, you're actually using arctangent divided by imaginary over the real number, right? So this is imaginary over the real number, and therefore you will get a value of a minus omega a. Okay, so how do we get the minus out? Because this minus sign, right? So you just bring the minus sign out. Therefore, you have a minus arctangent. Because sine and cosine, okay, and it's just a trigo rule, you will get tangent omega a. This is just a simple, very simple trigo rule, that's all. I believe you already know, so I don't go through. But nonetheless, you will get this, and then typically you will know that your phase angle is this value minus omega t, okay, minus omega a. So there will be a phase shift in terms of minus omega a, and then so also saying that this makes sense if you delay a signal, you're not changing the magnitude of the signal. If you remember back the phase angle, the Nyquist stability thing, okay, the magnitude is always 1 because you didn't change any magnitude. Okay, you're just simply um, changing the phase angle. Okay, as shown in the video previously at about here. You can see my transfer function is this, and then I put in the gain 7.5, right? So therefore, if you were to go through it, I didn't actually change the angles. I only changed the amplitude, as you can see, right? So the delay is simply only, actually this is not a good example. Okay, anyway, so the delay itself doesn't, as you can see, it does not contribute to the increase of the magnitude itself. Okay, just to let you know this is the case. So I repeat again, the delay doesn't contribute to the gain, or in other words, it doesn't contribute to the magnitude of the frequency. Okay, it doesn't contribute to the amplitude. So let's say this is the thing, right? If you have a delay, you are just only delaying in time like that. You will not increase. If this is the case, right? This graph, okay, this one is delay plus gain. Okay, so I just want to make sure you know this thing. Just a sneak peek before I go to other explanation. You see the Pardee approximation. You can see that there is a wow, you know. Okay, just to let you know, in the future you may actually need to study this also. So be warned, my friend, be warned. Okay, so just to show you in the Nyquist plot, okay, in the Nyquist plot. Okay, I have a certain transfer function, okay, we call it 15 over 6s squared plus 3s plus 2. This is actually in your lab, okay, in the lab if you remember. This is the same transfer function. Okay, now I sub in a different value of gain, and then let's plot this table and see the results, okay. So as you can see, the gain when it's 1.5, okay, so let me put this over here. Maybe it will be much clearer. Okay, so this is the gain. Okay, so the blue color is actually the 1.5 gain. Okay, I don't know whether okay, I cannot see the 1.5 gain anyway. So am I lagging? Okay, so never mind, it's there. But nonetheless, if you were to take a look, okay, 1.5, 2 and 2.5, okay, this is my gain. I mean, this is my k lah, okay, I times by multiplying the k, okay. So in other words, the whole block diagram will looks like this is a k, and then this is the g of s, and then this is the output, right? So I have a gain over here times the transfer function. This is exactly what I'm doing right now, okay. And then as you can see, if I were to zoom in this Nyquist plot, okay, this is a Nyquist diagram, okay, and then this is gain equals to 1.5. This outer layer is when gain is equals to 2, and the most outer layer is when gain equals to 2.5. So let's take a look in the delay part, okay. The only way we can look at delay is only when it crosses the stability margin, then I can only look at it. As you can see, if I were to click at this point, right, I cannot see the delay. But if, never mind. So if I were to click this point, as you can see there is a delay margin over here showing you. So if I were to take a look, okay, if I were to bring this thing over here, okay, so this is the yellow color one. As you can see, okay, let's start with the blue color one, okay, in order not to confuse you. So this is the blue color one, okay, untitled 1, untitled 1, untitled 3. So by the number, the smaller you are, the number of k, the smaller your k is lah. So in this case is 1, 2, and 3. So k equals to 1.5, k equals to 2, okay, k equals to 2.5 in this case. As you can see, the delay is 0.135, and as your k increases, your delay actually decrease. Okay, your delay actually decreases, and then it decreases more. So actually I can plot the delay now. So it's 0.135, 0.101, then 0.806, 0.0806. Okay, and then as you can see the frequency, okay, at this point the frequency is 1.99. Sorry. should be here. So this is the what I'm trying to plot the table is later I'll just show you the example. So I'm plotting the gain, phase, and frequency and delay. Okay, so the gain is the blue color, 1.5 is the blue color, 2 is this portion over here, this orange color line, and if it's 2.5 gain, it is this yellow color line. Okay, what I'm doing now. So what I'm doing now is actually to plot the table out to show you the results. So if its gain equals to 2, right, it's this orange color line. So therefore, as you can see, it's the frequency is actually 2.28. And then the frequency for this is 2.54. And then for the phase, okay, in degree, it's actually 15.4. And then 13.2 and 11.7. As you can see, yeah, so I didn't cheat the filling. So what can you deduce from here? When the gain increases, your delay decrease. Okay, your delay actually decreases, right? However, your frequency when your frequency increases, when your frequency actually increases lah, okay. So in order to be stable lah, okay. In order to be stable, this is the point. Okay, these are the 3 points. So as your gain increase, your frequency has to increase, your delay has to decrease, will decrease, and your phase angle, as you can see, will decrease also. So what can we deduce from this table? Okay, how do we link delay and frequency and phase? As you can see, what I have written over here, radian per second, degree. As you can see, if I multiply frequency times the delay, I can have my phase angle. Okay, in this case, this is degree lah, right? So I have to switch to degree first. So what I can do is to show you an example. So let's take 1.9 times 0.135. So this is the frequency times the delay. Okay, what do I have? Okay, so hold on a while. As you can see, if I were to 1.9 times 0.135, I will have 0.2565. Right, this is in radian. Right, this is radian per second times 1 over times second, sorry. You have a radian. So if you were to convert to degree, you will have 15.4 degrees over here. Okay, if you don't, so 0.2565 times 180 divided by pi. Okay, if you were to convert. Okay, this converting is only using 180 divided by pi, that's all. Okay, so what do you get? Okay, let's take a look. If I times 180 and then divided by 3.142, I have about 14. I should have put in 1.99 lah. Okay, that one decimal place is very critical. Okay, so let me retry it. Hopefully I can get the real answer. Okay, so this is 1.99. Let's take a look. If 1.99 times 0.135 okay, and then I times 180 degrees divided by 3.142. You see I have 15.39 over here. Okay, it's the same thing. Okay, so simply 1.99, I repeat again, it's 0.26865. 0.28685 radian. So if you convert 2.8685 times 180 degrees divided by pi, okay, this is what 26865 times 180 degrees divided by 3.142, which is the pi, you have 15.394. So this is the phase angle. Okay, so we can conclude that from this, if you have the frequency, okay, and you are given a delay, you can find the phase angle. Okay, so this is most likely a very important tricky case. Okay, this is a very tricky question. So it happen that in the test they ask you, you are dead. Okay, so you make sure you go and remember this date. Okay, so if you still don't trust me, let's try for this. Okay, let's try for for another value. Let's say we try for the gain is equals to 2.28, okay? 2.28 times 0.101, okay? What do I get? Okay, so 2.28 times 0.101, we have 0.23028. 0.23028, and then if I were to convert to degrees, okay, times 180 degrees divided by 3.142, you see I have 13.19, which is 13.2 degrees. So therefore, we can conclude that frequency times the delay will give you the phase angle. And this phase angle is actually the one that I have shown you, the one that I reduced for the gain and phase margin. Okay, where are we? I'm lagging, as usual. So this is the phase margin that I'm talking about, the phase angle. Okay? So I hope that I give you a very good concept of what is actually the delay and how do you use the delay to calculate certain things. So it's a very important thing. So I'll see you in the next video for performance criterion, and then after that summary. So I'll see you there.